Okay, so do you hear me now? Where?
Yes.
Yeah. So thank you for the introduction. I'm Joonwoo Bae from KAIST, Korea. So the first thing I'd like to do is to thank the organizers for giving me this opportunity. So I'm very happy to join this meeting. And also I'm very happy to deliver the recent work of my entanglement detection 2.0. So this work is done by collaborating with the people here, Dariusz Krunczynski in Poland, Torun in Poland, and also Beatrix Hismaier from Vienna. And also this work, I mean, the talk is based on the publication here, the mirrored entanglement witness, which has appeared in MPJQI last year. Okay, maybe I move to here. So yeah, so take-home message is the following. So maybe some of you are already familiar with these entanglement witnesses, and often entanglement witness corresponds to a hyperplane that separates some entangled state from separable state. Then often it is known that entanglement witness corresponds to a single hyperplane. And today the message that I want to tell you is that actually there's another hyperplane we can define from the same entanglement witness. So there is actually non-trivial upper bound to the entanglement witness. So that's the take-home message. And actually, witness can be non-linearized to improve the efficiency of detecting entanglement states. And the same applies to entanglement witness 2.0 as well. So this, yeah, I will come to the detail later. So the whole point is that I want to tell you about entanglement witnesses, but improve the version, which we call entanglement witness 2.0. So I will start from introducing entanglement witness, and then I will also explain the motivation and the details of our contributions. Okay. So let me start with the scenario of detecting entangled states. So maybe I will go in this way, so then you see the blocks. Yeah, so imagine, so suppose that there's a device which generates quantum systems. So every time the system generates row AB bipartite state and many copies, okay? And now we have a device which performs the measurement on these quantum states. And then now we want to know if the state is entangled or separable. So maybe to know that the entangled state is entangled is more important than to know the state itself, because entangled state is useful in general, also resource in quantum information processing. So then the question of asking if the state is entangled or separable, this is highly depends on our technology. The first scenario, or strategy number one, is that maybe we can assume that we have a power to apply collective measurement. Okay, so collective, in order to realize collective measurement, which means we perform measurement on m copies altogether, and for that we need quantum memory, which is a device to store quantum state in a quantum level for a while, and then we perform the joint measurement. Okay, and this is actually maybe the most difficult level in quantum measurement. The next one maybe a bit more feasible. Here we can remove the quantum memory, but still we need an operation to entangle quantum state to realize a joint measurement on different copies. So this is so difficult. And then the most feasible one is the local measurement and classical communication. So which means we perform measurement on individual copies, okay? And then according to measurement outcome, we may update our measurement device in order to choose a better measurement in the second copy. And then from the measurement on the second copy, we also update our measurement device and then to perform better measurement on the third copy, and so on and so on. And then this is actually local measurement plus classical communication. And then the same level of technology, so namely local measurement and classical communication, can also realize quantum state tomography. Okay, so quantum state tomography is a technique to verify what quantum state has been prepared here. Then after quantum state tomography, maybe we can perform we can apply the useful theoretical tools, for instance, semi-definite programming or P-not complete positive map to detect entangled state here. Okay, so if we assume our technology with local measurement and classical communication, then there are two possibilities. The first one is quantum state tomography, and the next one is just some strategy which is based on local measurement and classical communication. Okay. Yeah. And then, okay, so strategy one is clear, maybe because we perform all possible measurement and then we verify what quantum state is, and this tomography. And next one actually define, we can interpret as entanglement witnesses. So entanglement witness, yeah, I mean, theoretically, this corresponds to hyperplane that separate some entanglement state here from separable states. And I mean, technically, we have to define as a Hermitian operator, which give positive expectation values for all separable states, but negative for some entanglement states. And in practice, entanglement witness is simply an observable, which is Hermitian operator, a self-adjoint operator. And this can be decomposed in terms of P of M elements like this. So MK is a P of M element and CK is a constant, positive or negative, but you can find the CK from a given entanglement witness here. And then we perform measurements. So we perform an experiment, okay? And the experiment contain measurement setup with these P of M elements, which is from the entanglement witness. So then we have a detector, okay, that corresponds to a P of M element, and then we compute the probability distribution or the frequency on this detector, and that corresponds to this formula, trace P of M times unknown quantum states, and then we collect all these probabilities and make a complex combination according to CK, and then this give you the expectation value of the this observable, which is entanglement witness. And then from there, you only have to check if it is positive or negative. And it's negative, then you know the state is entangled, certainly. Okay? That's the strategy. And well, just formal definition of entangled state, I mean, at least in the bipartite state, we call the state is product if the state can be factorized into rho A times rho B. It's a separable, it's a complex combination of product states, or entangled if the state cannot be written in this form. Then, or operationally, we call the state cannot be prepared by LOCC. And in fact, this is a difficult problem to find the state is entangled or separable, because this is called the separability problem, which is the question of characterizing the border of separable states. But this is actually classified as NP hard, which is a difficult problem. In practice, so yeah, so as an example, so entanglement witness, this would be a good example for 2-qubit entangled state. Okay, so I just introduced an Hermitian operator, which is not positive, and identity times psi minus and psi minus, which is a singlet state. And this is certainly entanglement witness because first of all, for all product states, it give a positive number. Okay, so yeah, so maximum would be 1/2. Then if you multiply some separable states, and this part give you anyway 1/2, and the maximum with this one would be 1/2 over separable states or product states, and therefore this would be positive for all separable states. But if we compute the expectation value of this observable with respect to psi minus this entangled states, then it is minus 1/2, and therefore which is negative, then we can conclude that the state must be entangled. So this is an example, and experimentally, how can you realize this entanglement witness? Yeah, so just this is an observable, and therefore you can factorize this witness into local observable for 1/4, and this is a mixture of identity and Pauli matrix is XX, YY, CZ. Okay. So then you realize this observable in experimental here, and then make a complex combination of the these expectation values. Then you can construct this one, and which tells you whether the state is entangled or separable. Okay, so yeah, so now we limit our technology, which is the most feasible way, state preparation and the measurement on a single copy level, and then we make a post-processing with the measurement outcome, and from there we want to conclude state is entangled or separable. And one way to do is entanglement witness, which separate some entangled state from which distinguish some entangled state from separable states, and therefore this conclude entangled state without any ambiguity. And the implementation again is a factorization into local observable here. Okay. So given witness, one has to prepare this number of measurement. Okay. And then I think I don't have to repeat this one. And then yeah, now just let me summarize the entanglement detection scheme in a single run. So suppose the state is known, suppose the state is given, okay, and it's important assumption that we don't know the state yet, okay. So state is unknown states, but maybe we only know the dimension of the states, and therefore we can construct this entanglement witness to detect entanglement existing in the states, and then we perform experiment, okay, and then we know the expectation value, and if negative, then certainly entangled, and positive or zero, then we don't yet conclude anything. So again, experimentally, we perform measurement here, and then collect all the probabilities, and then yeah, from the probabilities, we make complex combination of the not the complex combination, but linear combination of the probabilities that corresponds to expectation value of an witness. So yeah, actually, so this blue box is a certain experiment to find the probabilities or frequencies here. Yeah, and then now one can argue, maybe suppose you're an experimentalist, okay, then you can argue that how many detectors I need. This is actually important because as I explained here, okay, so one witness constructs this number of measurements, and then maybe we fail because in the end, if the expectation value is positive, that we cannot conclude anything, then one has to apply different entanglement witness, but then the witness tells you the number of POVM elements you have to implement, and overall, all the POVMs are more than what you needed in the state tomography. So maybe then to realize entanglement witness is more expensive than state tomography. This is not what we wanted yet. Okay? So the whole scenario is that state is unknown yet. Then first you perform state tomography. Once you perform state tomography, then you know the state. Then, well, although the problem itself is NP hard, but you can apply many known theoretical tools. So positive maps, there's a huge literature about the positive maps, and moreover, if you consider 2x2 systems, and the partial transpose is a necessary and sufficient condition to detect entangled states. And also there is a useful technique, SDP, which can also efficiently detect entangled states. So here the quantum process, quantum state preparation and measurement, and then state tomography, and then this classical process, which is free, okay, well, which is not very expensive. And then, or we don't want to know the state, but we just want to know if the state is entangled or separable. Then the most feasible way, okay, here, well, we have to implement entanglement witness, which is just a observable, and then from there we conclude the state is entangled. Then yeah, we get the answer here. Okay. So if I can tell you the advantage of entanglement witnesses is that entanglement of unknown quantum state can be actually detected, and that's the advantage. But that one important argument or drawback is that it's not so clear how many measurements you need to realize an entanglement witness. So again, we can also keep asking, is entanglement witness is really useful because it merely corresponds to one single hyperplane here, and but we have a lots of entangled state which are not detected by this witness. Okay? So now the first result I want to present is that entanglement witness can be compressed to a single line, or in other words, entanglement witness can generate another entanglement witness. So simply saying, before we had just one bound here, okay? So for all separable states, a single entanglement witness should satisfy these bounds, but then I can also provide another bound here, upper bound. Then once you perform experiment to estimate expectation value of this one only, then you have two chances of applying your experiment to check the lower bound and to check the upper bound. And later I will show you this lower bound corresponds to this witness, and upper bound corresponds to this witness, and they are independent and they're complete different one, but they compressed into single line here. Okay, but let me go on detail. So the main technique I want to present is here SPA. It's called structural physical approximation. Okay, so let me go through what it is. It's a very simple one. So given witness, okay, which is non-positive operator, but then we have prepared another one which is which is identity operator, and we admix these two operators such that W tilde becomes positive. Okay, so then after and this process is called SPA. Okay, and because we transform non-positive operator into positive operator, and in this sense we call physical approximation, and the identity operator doesn't change the structure of eigenvalues, and therefore structure is preserved in this sense. So then we call structural physical approximation. So we are looking for the effect. We are looking for P star in such a way that the effect of identity is the minimal, and therefore we choose a minimal P, okay, such that lambda tilde, no, W tilde is positive, okay. And then, yeah, one has to look at the detection scheme. So before we had a detection scheme for all separable states, the witness should give a positive expectation value. And now we translate this one in an equivalent way in this form, because W tilde is now a positive operator. So the proof is very simple, in a simple line. Given witness, okay, I construct this guy, okay, and apply separable states. Then, well, because W tilde is given here, and then we have a linear combination, and well, this part is certainly 1 divided by d square, and this one is non-negative because we apply separable states, and therefore we have these bounds. So p star divided by d square is the lower bound provided by all separable states. And yeah, so detection scheme now is translated to this inequality. Okay, so well, I didn't do anything. I didn't do anything meaningful. Just I translated this detection scheme into this operator after SPA. Okay. And let me introduce another one. Let me classify SPA into two classes. The first one is PSPA, and the other is NSPA. Okay, so PSPA is exactly what I explained. So given witness, I admix this identity operator to make it positive, and then I have a detection scheme here. Okay? And negative operator, a negative SPA is the following. So here I do the same thing here, okay? But now I choose my Q larger than 1, which means this part is negative, and this becomes more dominant. Then I will look for maximum Q, okay, so larger than 1, such that this becomes positive. Okay, this is actually possible because W is non-positive operator, okay, and then it has positive projector and negative projector, and here I use the negative projector, and here I use the positive projector, and then with this NSPA, okay, so negative SPA, I can translate this detection scheme into W plus minus, okay, in the following way. So W tilde minus, okay, has a decomposition here, okay. Then, well, I just apply separable states, then this becomes negative because Q is larger than 1. And for all separable states, this part is positive, okay. And this one is fixed Q star divided by D square. Overall, this part is negative, and negative for all separable states. And for some entangled state, this becomes negative, and then whole 1 minus Q star and trace W row entangled, which is positive. So so whole quantity is bounded upper by this number Q star divided by Q star divided by D square. Okay. So well, I mean, I didn't do anything. Just what I did is just given Whitney's. Okay, I manipulated with identity operator, and here sometimes I choose P star, which is less than 1, but minimum. Okay, P star, which is less than 1, and I choose minimum P, and sometimes I choose a maximum Q, which is larger than 1, and I construct this one. Okay, and then initially I have this condition for entanglement detection, this condition for entanglement detection, and then I can translate the condition into equivalent one like this and like this. Okay, so far, okay, I didn't do anything. I just given Whitney's, I play with them, and I derived 3 equivalent and different conditions. Okay, well, maybe the same condition because they are equivalent. Okay, so this condition detect some entangled state, and those entangled states are exactly detected by this scheme as well, and this scheme as well. And here W plus minus tilde, these are both are positive operators, and they are obtained from W in a different way. And the first one is P star, and the other one is NSPA. Okay. So now, yeah, again, the summary, given W and common Whitney's, I construct 2 operators which are both positive, and this is the same condition I have here. Okay. Now I'm doing in the other way around. Okay. So here, given Whitney's, I generated 2 positive operators. Now what I'm doing is that given positive operator, I may derive 2 entanglement Whitney's. Okay. So how can I proceed? Suppose W tilde is given. Okay. Suppose W tilde is given, which is W plus tilde or W minus tilde. Okay. So I put this equality, and then from W tilde, I may derive W here. Okay, by subtracting identity operator from this guy. So my job is to find this decomposition. The second way, the second one, given this guy, okay, I subtract this operator to construct this guy as well. Okay, so yeah, I subtract this guy identity operator with a P less than 1, and the next time I subtract this operator with a Q which is larger than 1. Okay, then I can derive 2 Whitney's, W and W. Okay, and because they are different, I named it W plus and here W minus. Okay, so now what I did is that given I choose just positive operator. Okay, from there I subtracted identity operator with a small portion and with a larger portion in order to derive 2 entanglement Whitney's. So I generated actually 2 entanglement Whitney's, W plus and W minus. Okay. So now I can summarize. Okay, then the detection scheme, this guy is this guy W plus is translated into W in terms of W tilde. Okay, which is this one. Okay, lower bounded by this number, and W minus, which is derived from W tilde. The condition is translated to this guy, which is bounded upper by this number. Okay, and overall I summarize in this way. So if you give me positive operator W tilde, okay, then I subtracted the identity operator with a small portion and larger portion then I can derive two entanglement witnesses, W plus and W minus, and then I put the entanglement detection condition in a single line in terms of lower bound and upper bound. Okay, so and then upper bound is equivalent to entanglement witness W minus, and the lower bound is equivalent to entanglement witness W plus. Okay, so simply saying I have now I have two witnesses, but I have a single quantity, and this single quantity can be used to detect entangled state using twice. I have two chances to test the entangled state here. Okay, so I can say I have improved the efficiency of detecting entangled state of entangled witnesses. Okay, so here I have a witness upper and lower bound for W tilde, which is the positive operator, but I can actually translate this one into single entanglement witness, which is positive for all separable state, but it has a non-trivial upper bound for separable state as well. Okay, and the upper bound is equivalent to entanglement detection scheme by some other witness W plus here. So in picture, okay, so before we have known witness corresponds to this line, okay, so therefore we can detect entangled state above the line, and now I have derived another line which is non-trivial, and we can detect also entangled state here. Okay, so now entangled witness is twice more useful than we thought before. Okay, and this is to take home message. In summary, just the technical part again. Yeah, summary, maybe it's better to look at this one. So actually, given witness and some other witness W prime, they are related in this way, okay? That you can always find two number and N prime that connect these two witnesses, okay? And then you can also find another positive operator here. It gives you lower and upper bound, and each bound corresponds to detection scheme of W and W prime, okay? So yeah, so if you give me one entanglement witness, I can generate another entanglement witness for free, and I can compress these two expressions into single line, so that once I estimate this number, I have two chances of detecting entangled state using lower and upper bound both. Okay? And now I can give an example. For instance, here W plus and W minus. Okay, and W plus can detect states in this form. 5 plus is a 0, 0 plus 1, 1, which is maximal entangled state, and 5 minus is the 0, 0 minus 1, 1. Okay, and I can tell you that no entanglement witness can detect both states at the same time. Okay, but now I construct W tilde. I can find lower bound here and upper bound here. Then I can detect two states at the same time using just one experiment that estimate expectation value of W tilde. Okay, so I have clearly this example show you that two entanglement witness can be realized at the same time. And for instance, and also one more, W plus and W minus, they are connected by partial transpose. So physically, they can never be detected at the same time. But now I can tell you that realizing this guy, you can actually detect both states at the same time. Okay. So, so in summary, yeah, if you give me some positive operator which can be decomposed into P of EM, then I call just P of EM cloud, and this corresponds to entanglement witness. Okay, so maybe so if I in a lecture, maybe if you ask me what is the way of detecting entangled state? Okay, then in the previous maybe one has to go through very difficult mathematics, for instance, positive but not complete positive map, and there's a one-to-one correspondence between there is a Choi-Yamakowski isomorphism between positive but not complete positive map and bipartite operators and so on, and therefore all these constructions justify entanglement witnesses. Okay, and yeah, so therefore steps to go to entanglement witnesses is actually far. But now I can tell you that no, you don't have to know all of these mathematics. You just collect the positive operator and compute these two numbers. Okay, then is realize two entanglement witnesses at the same time. Okay, so this is the result. And the next step. Okay, so now I just collect just P of M elements, and from there I can tell you what is the bound here, upper and lower bound, and from there I can detect entangled states. Then the question now is, I want to make smooth transition from entanglement witness to quantum state tomography, because quantum state tomography, we apply all possible measurements and we verify quantum states. Okay, so the number of POVM elements we apply in state tomography should be the maximal number. Okay, so here what I want is that we apply smaller number of POVM elements, which is not tomography complete, which is a subset of the quantum state tomography, and from there we want to detect a part of entangled states, and so on and so on. And if we increase the number of POVM elements, then we may be able to detect all possible entangled state, which is equivalent to state tomography. So that's the goal. And then the measurement elements here is actually mutually unbiased basis or symmetric information incomplete measurements. Okay, so MOP basis, MOP measurements or SIG measurements. Okay, and here we apply the subset of MOPs and subset of SIGs. Okay, which are not informationally complete, so they cannot construct a quantum state completely, but they can detect some entangled states. That's what I want. So now, what I do, I collect the measurement outcome from mutually unbiased basis or symmetric and informationally complete measurement. Okay, so then collect the measurement element here. Okay, no probabilities here, and from there I can compute the upper and lower bound, and m is the number of MOPs I apply. Okay, so yeah, so this is some picture I'm expecting. If I apply a whole number, okay, m equals to d plus 1, then I have a tight bounds for separate states. But if I apply less number of POVM elements, then I have a non-tight bounds here and here. Okay, so now let's try in the case of dimension 2. So if I collect, okay, so I3, I2 is the collection of two. Okay, I2 is a collection of 2 MOPs, and I3 is a collection of 3 MOPs. In dimension 3, we have 3 MOPs, and therefore this is the full set, and we have bounds 1 and 2. One is the lower bound, and 2 is upper bound for all separable states. And violation of that, detect the entangled states. And if we apply less number of MOPs, say 2 MOPs, then we have a 0.5 and lower bound and 1.5 upper bound. So all these bounds are satisfied by all separable states, and violation of that detect the entangled state. And here you see lower bound is not so tight, and here also not so tight. And if you increase the number of measurements, and if you increase the number of POVM elements, then you have a better bounds here. Okay, the same you can also observe in t equals 3. In t equals 3, we have 4 MOPs and the same number 1 and 2, and the number here decrease and also decrease here. Okay? So yeah, the first in dimension 3, suppose you have just 2 MOPs and you cannot construct the quantum states, and therefore you are not able to find the quantum states, but you can apply the measurement to detect entangled states. And if you apply one more measurement, one more MOPs in the measurement, then you can detect a larger set of entangled state, and increase one more, you perform state tomography, then you verify all entangled states. Okay, and t equals 3, it equals 4, we can do the same. Okay, so you see the behavior. Okay, here tight and less tight and less tight and less tight. Okay, and so on. Okay, so in dimension 6, we only know 2 MOPs so far, and it's one of the major open questions in quantum information theory, whether we have a more number of MOPs or not. Okay, so these are the bounds we have found in t equals 6. If we apply, so if we apply 2 MOPs, then you have a lower bound 0 and 1.66 upper bound, and 3 MOPs, then you have a 0.1479 and 1333. Okay, since dimension 6, we only know 3 MOPs so far. We cannot compute more, but yeah, but 3 MOPs are still useful to detect some entangled states. Okay? And then there's a scheme to non-linearize this linear witness. by subtracting these expectation values, and then you can, so given W plus, you can non-linearize these Whitneys in this way, okay? And here you have the subtract here, and the other Whitneys that give you upper bound, here you have to add this value in order to non-linearize like this, okay? And if you apply minus here, then this one, the curve doesn't make in this direction, but in this direction, so it's inefficient. That's why we have to choose minus here and plus here. Okay? So in summary, okay, before our results, we have known that entanglement Whitneys corresponds to a single hyperplane that separates some entangled state from separable state here, okay? And today I've shown that, or the same measurement scheme, okay? So this measurement scheme corresponds to this scheme of entanglement Whitneys. And today I've shown that the same measurement setup can actually detect some other entangled state here, okay? And therefore this measurement setup corresponds to two entanglement Whitneys. So I've shown that entanglement Whitney, I've shown that you can actually detect a larger set of entangled state from the same measurement setup, okay? Maybe in the future, it would be possible to open more boxes, meaning that a single measurement setup can detect an even larger set of entangled states, okay? So I leave it open, and also in the future, it may be automatic to non-linearize the given linear Whitneys. Okay, so that's all I want to tell you, and I've explained entanglement Whitneys, which is the most feasible way of detecting entangled state, and then I also made a smooth transition from entanglement Whitneys into state homography using quantum 2 design, where I applied MOPS and 6. And also, one important message I want to tell you is that in order to learn about entanglement Whitneys, now you don't have to go through positive, but not completely positive map. Just collect all your possible measurements, and from there, compute the upper and lower bound satisfied by all separable states, and that actually give you the scheme, or maybe the easiest scheme of detecting entangled states. Okay, and in the future, of course, I want to keep opening the boxes to find that this device measurement setup is even more useful to detect entangled states. Okay, and again, this is the last message I want to tell you. I mean, through this project, I've learned that entanglement Whitneys are more useful than I thought before. Okay, so we have a lower bound for all separable states, but actually there's another. I mean, maybe we didn't know, but non-trivial upper bound satisfied by all separable states, which are also useful to detect entangled states. So that's all, and thank you very much for your attention.
Okay, thank you, Professor Bae. Now the floor is open for questions. Any questions? Yes, Professor Liang.
Hi, Joonwoo. This is Yong Chen. I have a couple of questions. So the first one is more on clarification. Can you go back to slide number 40?
40, see.
So you say that when you increase the number of MOPs that you use, then it becomes tighter. It's not clear to me in what sense it's tighter.
Okay, so so maybe it's better to look at this. Okay, so if you apply all MOPs here, then then we okay. So lower bound corresponds to some Whitneys, and
yes,
so as well, and this the Whitneys corresponds to the lower bound here is more optimal. Actually, can detect a larger set of entangled state than the Whitneys corresponds to these lower bounds.
Right. Okay,
Yeah.
but it's not obvious just from the inequalities themselves, I guess.
Okay. So then, for instance, I have an entangled state, okay, and which gives the bounds 0.7, okay.
Right.
And which is violated by this Whitney, this lower bound, but 0.7 is satisfied by this inequality. So 2 mobs cannot detect that entangled state, but if I apply 3 mobs, then I can detect that entangled state.
Okay, fine. So another question that's kind of related, which is that do you know whether there's any example whereby the weakness is non-trivial if you look at, say, the lower bound, but it's trivial if you look at the upper bound? Meaning that could it be that there's some hyperplane in the space such that in one direction it corresponds to non-trivial weakness, but the other direction it simply cannot be violated by entangled states or by any quantum states? So that there must be some kind of flat boundary. Do you know of examples like this?
No.
Is it possible for this to exist at all?
So, okay, I actually, we mentioned in our, so here 2 witnesses, they are actually non-optimal, and therefore this can detect, so this witness can detect this entangled state, and this W minus can detect this type of entangled state. But once I make it W plus optimal, and then the other one, a mirrored one, W minus, is a trivial one, which is positive operator. Yeah, that is what happened in dimension 2. But the higher dimension, there's a more structure, so this is not necessarily true. But at least dimension 2, I can tell you that as soon as one witness is optimal, its paired one W minus is a trivial one. This I can tell you. But apart from that, I don't know. No, I don't know. Yeah, I don't know. Yeah.
So you mean in the 2 qubits case, if one of these witnesses is optimal, has been optimized, so that it touches the boundary of the separable set, then when you shift this hyperplane to the other side, it will be trivial. Is that what you are saying? Exactly.
Yeah. So it character. Yeah. So if I make it, maybe I can make it this optimal, and the other one becomes like this.
So this is always the case for 2 qubits. Oh,
yes.
I see. Thanks.
Yeah, I'll say this is actually the property from the partial transpose. Yeah.
I see. All right. Thanks very much. Yep.
Thanks.
Okay. Any further questions? Okay, if there's no any questions, then let's thank Professor Bae again.
Thank you for your attention. So I have to stop sharing.